All right, so here we have that problem again, but we're going to add friction to the surface. Kind of a generic type of problem is solve for the acceleration and solve for the tension. So we're going to go ahead and do that. So draw our free body diagrams is our first step. Right? So on block 1, we have the normal force going upwards. We have gravity going downwards, and we have the tension going to the right, but now we have friction, and that is going to act opposite its direction of motion. On block 2, nothing has changed. It wasn't touching the surface, so those two forces are what it was in the previous solution. We're still making this our positive direction, so this one is positive, this one is negative. This tension is positive, that friction is negative. Okay, so we're going to write our sum of all forces equations for each of these. Sum of all forces for block 1 causes it to accelerate, and then we have the right minus the left. Tension minus friction equals M1A. Right? Since this diagram did not change, the equation does not change. M2G minus tension equals M2A. All right, so we can see that from the previous problem, we added a force to the diagram. All it does is add that force into the equation. All right, so process still the same. We're going to add those up. Right, so that and that combine, we're going to add those together. So we have T minus friction plus M2G minus tension. And then we add the right-hand sides, and the acceleration is the same, so we can factor that out. When we combine those, we have T minus T. It cancels those two forces out. So we have our M2G minus friction is going to equal the sum of the masses times their accelerations. All right, so usually at this point, well, not usually, at this point, we were able to plug in our numbers and get our acceleration. Here, we don't have all of the numbers. We need that frictional force. So this is where we're probably going to have to use that fun equation because we're given the mu. So if there's that mu given, we have to use the fun equation. I'm just going to bring it on up here. All right, we're going to have to utilize these forces in that direction now for the fun equation. What we can see is that if we added up those y components, right, it's not accelerating up and down, which means that those have to be balanced. If they're balanced, then the normal force equals the weight. So I'm going to just make a note of that the normal force is equal to the weight of mass 1. All right, let's continue to solve for our frictional force using our fun equation. Since the normal force is equal to this, I'm going to plug that right into here. So I have friction is equal to mu times M1G. I know mu, I know M1, I know G. I can actually get that number right now. Not going to do it. I'm actually going to try to move through this with the least amount of numbers that I have to plug in as possible. So I'm going to plug in what friction is equal to in terms of its variables into that part of the equation right there. Okay. So I have M2G minus mu M1G, and that's going to equal M1 plus M2 times A. All right, now I know all of those numbers. I can solve for the acceleration. Need more space. Bring that up here. So that acceleration is equal to M2G. So that's going to be 1 kilogram times 9.8 meters per second squared minus mu, which is 0.1, times mass 1, which is 2 kilograms, times G, which is 9.8 meters per second squared, all over the sum of the masses, 1 kilogram plus 2 kilograms. And that is it. All right, so acceleration is equal to 9.8 newtons minus 0.1 times 2 times 9.8 gives us 1.96 newtons all over 3 kilograms. Do that math, and you get an acceleration of 2.61 meters per second squared. And it should make sense that this scenario is going to accelerate at a lesser rate than this one since there is a resistance force. All right, and the last step is to solve for the tension. We do that the same way we did before. We take this acceleration and we plug it in to one of these two original equations. Again, one of them might be easier than the other for you to choose. Doesn't matter. I'm going to go with this one right now. Bring that over. I'm going to manipulate this for t. So I have to move the t over here and move the m2a over here. So I have tension is equal to m2g minus m2a. And you can see that, maybe think about it this way. You can factor out the m2. So it's really a difference between the acceleration rate of gravity and the acceleration rate of the system that determines what the tension is. So we have 9.8 minus 2.61. Multiply that by mass 2, which is 1. We get a tension of 7.19 newtons. And that should be greater than what we got before, which it is. All right? There's that extra resistance there. So if we just think about it this way, that block is accelerating down at a lesser rate. This upward force has to be greater than what it was here because the downward force did not change. All right, so there is the example. Adding friction to it adds an extra force, adds an extra couple steps, but other than that, the process is still the same. So I'm going to try one more example when we add inclines into this.